Section 7.4 is arc length and surfaces of revolution. We're going to start by learning how to compute the arc length of a curve, and then we're going to look at finding the area of a surface of revolution. So to begin with arc length, what we say is given some graph, and we're going to call this graph F, and the graph of F consists of connected line segments. To find the length from A to B, so let's say that this right here is A, and we want to find the length from A all the way to B. We're going to call this here B. What we could do is add up a number of line segments. So let's say that I call here x sub 1, x sub 2, x sub 3, and we could say to find this length, we could find the length from A to x sub 1, from x sub 1 to x sub 2, from x sub 2 to x sub 3, and from x sub 3 to b, and we could use the distance formula to find the length of each one of those line segments and add all of them up. So the arc length formula is coming from this distance formula and integration. Let's take this little bit here and blow it up so we can come up with the formula for arc length. If we redraw this graph, it would look something like this. This is still A, and this is still x sub 1. If we wanted to find the length from A to x sub 1, and we made this triangle in here, this right triangle, notice that the distance from this dot to the end of that triangle would just be a change in y, and the distance from this point on the triangle to x sub 1 is just a change in x. We're going to call this here the change in arc length, and we're using the letter S for arc length. Well, if we have a right triangle, we know by Pythagorean theorem that the change in S squared has to equal the change in y squared plus the change in x squared, which again comes from Pythagorean theorem that states a squared plus b squared equals c squared. Well, if I divide both sides by delta x squared, so I'm going to divide everything by delta x squared, I can then rewrite this as delta s over delta x squared equals delta y over delta x squared plus 1. Taking the square root of both sides to solve for delta s over delta x, I'd have delta s over delta x is equal to, and I wouldn't write plus or minus here because we're looking at length, and length is not negative, the square root of delta y over delta x quantity squared plus 1. Well, if I wanted to find the arc length S, we would have to integrate both sides here. So if we integrate this, we end up with S is equal to the integral from A to B of the square root of, well, delta y over delta x can be rewritten as dy dx quantity squared plus 1 dx. So that is the formula for arc length. We're going to look at two separate formulas for arc length. One of them when we're given y as a function of x, and the other one when we're given x as a function of y. If you're given y as a function of x, and that function is smooth on the interval from a to b, then we say that the arc length of f from a to b is little s is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. Now this textbook uses the letter s, the lowercase letter s, to represent arc length, but you'll see me use the letter L so that we can make sure that we're dealing with arc length and not surface area. Surface area uses a capital S. Similarly, if you have x as a function of y on some interval from c to d and it's smooth, then the arc length there would be s is equal to the integral from c to d of the square root of 1 plus g prime of y squared dy, and again I'm going to use the letter L here. These formulas are essentially the same thing. The formula for arc length is always just going to be that your arc length is equal to the integral from a to b of the square root of 1 plus the derivative of that function squared, and then dx if you're given y as a function of x, or dy if you're given x as a function of y. Let's look at the first few examples that ask us to find arc length. Find the arc length of the graph of the function over the indicated interval. We have y equals 2x to the 3 halves plus 3, and we're told to look at the interval from 0 to 5. We know our a and our b, and we have our function. Now this is a function of x, so I know I'm going to be integrating with respect to x. I need to find the derivative squared. So I'm going to find the derivative of the function, square it and add 1, and then place it into my arc length formula and integrate. This is why we know that y prime here, the derivative would be, well, 2 times 3 halves is just going to be 3. X, raise it to 1 less, and we get 1 half. The derivative of 3 is 0, so we don't need to write that. Now we're going to take that derivative and square it. If we take 3x to the 1 half and we square it, we end up with 9x. Now we have to add 1 to it. So y prime squared plus 1 is just 9x plus 1. Now we're going to put that into our formula. Arc length is equal to the integral from a to b, in this case 0 to 5, of the square root of 1 plus derivative squared. Well, here's our 1 plus derivative squared, in this case 9x plus 1, and we're integrating with respect to x. The square root function we know is the same as the 1/2 power, so we're going to rewrite it as the 1/2 power. And then we're going to use a u sub to work this out. If u is equal to 9x plus 1, because that's what's being raised to a power, then the derivative du would equal 9 dx. I don't have a 9 dx, I only have a dx, so I divide both sides by 9, and I get 1/9 du is equal to dx. Therefore, we know that our arc length is equal to the integral from x equals 0 to x equals 5, because I didn't change the limits of integration to u, of u raised to the 1/2 power, and then my 1/9 du. Moving over to the right-hand side, we have L equals 1/9. If I integrate u to the 1/2, that becomes 2/3 u to the 3 halves. And this gets evaluated from x equals 0 to x equals 5. Cleaning this up and then getting out of u's and back into x's, I get that arc length is equal to 2 over 27 times, well, u here is going to be 9x plus 1, and that gets raised to the 3 halves power, and this gets evaluated from 0 to 5. Plugging in those limits of integration, 2 over 27, and then if I plug in a 5, 9 times 5 is 45 plus 1 is 46, so I have 46 to the 3 halves, minus, and if I plug in a 0, 9 times 0 is 0 plus 1 is 1, and 1 to the 3 halves is just going to be a 1. Rounding our answer to 3 decimal places, we'd have 2 divided by 27 times, and this is 46 raised to the 3 halves power, and then minus 1. We hit enter and we end up with 23.036. So our arc length here, L, is approximately 23.036. Let's look at our next one. We have x equals 1/3 square roots of y times y minus 3, and we're told that y is trapped between 1 and 4. We have our a and our b again, and we have this function, which is x as a function of y. So I know I'm just going to be integrating with respect to y, and my arc length is still the same formula. It's still the integral from a to b of the square root of 1 plus the derivative squared, and again, dx if you're a function of x, or dy if you're a function of y. Since we are a function of y, we're going to be using our dy. Well, the first thing I want to do is find the derivative of this, but before I find the derivative, I'm going to rewrite the radical and distribute just so that finding the derivative is a little easier. So we're going to say x is equal to 1/3, and then this is y to the positive 1/2 times y minus 3. If I were to distribute here, x would equal 1/3 y to the 3 halves, and then minus, and that's just y to the 1/2. Now let's take the derivative. X prime here would be 3 halves goes and multiplies the front, and I have 1/2 y to the 1/2 minus here 1/2 y to the negative 1/2. Now before I square this, I'm going to get back into radicals, and I'm also going to get a common denominator. Writing things in radical form and without negative exponents, I have the square root of y over 2 minus 1 over 2 square roots of y. Because this 2 is already in the denominator, and remember y to the 1/2 is just the square root of y. Again, this 2 is in the denominator. This ends up in the denominator because it's a negative exponent, and remember the 1/2 power is just the square root. So what I want to do now is find a common denominator. Well, the common denominator between these two is going to be 2 square roots of y. So I'm going to have to multiply this fraction here by the square root of y. I end up with x prime is equal to, well, the square root of y times the square root of y is just y minus 1 over 2 square roots of y. Now that I've got a single fraction, I'm going to go ahead and raise it to the second power. So I'm raising this side to the second power and this side to the second power. X prime squared is going to equal, well, if I take y minus 1 and I square it, so think you're writing it twice and foiling, you end up with y squared minus 2y plus 1. And then if I take 2 square roots of y and I square it, well, 2 squared is 4 and the square root of y squared is y. Now what we need to do is add 1 to it. So x prime squared plus 1. You have y squared minus 2y plus 1 over 4y plus 1. Well, in order to add fractions, you need a common denominator. The common denominator is going to be 4y, so I need to multiply this fraction over here by 4y. You have x prime squared plus 1 is equal to y squared minus 2y plus 1 plus 4y all over 4y. Combining like terms there, I end up with y squared plus 2y plus 1 all over 4y. The last thing I can do before I put this in my formula is realize that this guy here can be factored. That's a perfect square trinomial. It factors as y plus 1 quantity squared, because y plus 1 times y plus 1 is going to give me that y squared plus 2y plus 1. Now we're going to put that back into the arc length formula. We know that L is going to equal the integral, remember it's from 1 to 4, of the square root of y plus 1 squared over 4y dy. I am allowed to distribute the square root to both numerator and denominator, so I have the integral from 1 to 4 of the square root of y plus 1 squared over the square root of 4y. Well, the square root and the square here cancel, and it's just y plus 1 because my limits of integration from 1 to 4 are positive, so it remains positive y plus 1. And then the square root of 4y is just the square root of 4, which is 2, and that's y to the 1/2. Well, 2 down here is in the denominator, but it's a constant multiplier. We can pull that right out of the integral. And then I'm allowed to put each term over y to the 1/2. So y divided by y to the 1/2 plus 1 divided by y to the 1/2. And I can reduce this and then integrate. So L is equal to 1/2 times the integral from 1 to 4. Y divided by y to the 1/2 reduces to y to the 1/2. And then this guy here, I can write it with a negative exponent so that it's easier to integrate. Integrating, we get the integral of y to the 1/2 is 2/3 y to the 3/2. The integral of y to the negative 1/2 is 2 y to the 1/2. And this gets evaluated from 1 to 4. Plugging in those limits of integration, 2/3, 4 to the 3/2 plus 2, 4 to the 1/2 minus 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2. Plugging this into a calculator, we end up with 1/2 times 2/3 times 4 to the 3/2 plus 2 times 4 to the 1/2, and then minus, and 1 to the 3/2 is just going to be 1, so we'll just say 2/3, and this should have been a 1 to the 1/2, not a 1/2 to the 1/2. So when we plugged in a 1 here, this should have been 2 times 1 to the 1/2, and 1 to the 1/2 is just going to be 1, so I'm just going to say plus 2 over here. Hit enter and then make this a fraction, and we end up with our arc length is 10/3. So our arc length here is 10/3. Let's look at our last arc length problem. We have y equals the natural log of the cosine of x from 0 to pi over 3, and again we're asked to round to 3 decimal places. Well, the first thing we have to remember is the formula, which is L equals the integral from a to b of the square root of 1 plus derivative squared, and then either dx or dy. Since this is a function of x, we're integrating with respect to x. This is my a and this is my b. So now let's figure out what is the derivative, and what is that derivative squared, and what is that derivative squared plus 1. If y is equal to the natural log of the cosine, we'll recall that the derivative of the natural log of u is equal to u prime over u. In this case, my u is equal to the cosine, so the derivative of the natural log of the cosine would be the derivative of the cosine, which is negative sine of x, over u, so over the cosine. Well, negative sine over cosine is just negative tangent. Now I need to square both sides. So square this side over here and square this side over here. Well, negative tangent squared is just tangent squared of x. Now add 1 to it, and you have tangent squared of x plus 1. Well, tangent squared of x plus 1 is just a Pythagorean identity. That's equal to the secant squared of x. So y prime squared plus 1 is equal to secant squared of x. Coming over here, we know that our arc length is going to equal the integral from 0 to pi over 3 of the square root of secant squared dx. Now the square root of secant squared will cancel with the square root and the squared, and it remains as positive secant because 0 and pi over 3 are in the first quadrant, and secant is positive in that first quadrant. Therefore, we end up with the integral from 0 to pi over 3 of the secant of x dx. Well, this is basic form. That integrates as the natural log of the absolute value of the secant of x plus the tangent of x, and this gets evaluated from 0 to pi over 3. Plugging in those limits of integration, we end up with the secant of pi over 3 plus the tangent of pi over 3 minus the natural log of the absolute value of the secant of 0 plus the tangent of 0. Well, the secant of pi over 3 is just 2, and the tangent of pi over 3 is the square root of 3. The secant of 0 is 1, and the tangent of 0 is 0. So here we have the natural log of 1, but the natural log of 1 is 0, so we don't need to write that. So the only thing we need to put in our calculator is the natural log of 2 plus the square root of 3. Grabbing that calculator, the natural log of 2 plus the square root of 3. Hit enter, and to 3 decimal places, we're looking at 1.317. Our arc length is approximately 1.317.